Welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. We are in the middle of our discussion of population activity, and we need just to do a little bit more of math to continue. Our aim is to predict the population activity just from neuronal parameters and the connectivity parameters. The question is, can we do this? Well, for time-dependent input, it's sort of difficult. But for stationary input, yes, it's possible. To do this prediction, we will exploit that all neurons receive the same input current, and it's the population activity which drives this input. And from this input, we want to predict the population activity. So we get in a closed loop. And how to do this? This is the topic of this section. So, our assumption now is that we work with a stationary state. This implies that this activity is not time dependent, but is constant. It's constant at its value A0. As a result, I can collect this integration, alpha of s ds. A0 no longer depends on time. There's no s anymore. So I can write this alpha of s ds. And I still have the factor in front, and I still have a potential external input, which I assume to also be constant, no time dependence. Okay? Now just let us define a parameter q equal to alpha of s ds, and so we have the result that j0 q a0 plus I0 external is the total driving force. And this is my first equation, which I will use in a minute. Now, this is my input. This input will drive my neurons. Now, what happens if you drive a neuron with a constant input? Well, let's just draw here the total input, I0, constant input, and let's draw here the firing rate. Let's call it nu. So this is the frequency of firing, and this is the current. So it's frequency versus current, or Fi curve of a neuron. So if I give a high current, strong constant input current, the frequency of firing is high, which means as a function of time, the neuron will emit many spikes. If I give a small input current, the neuron will emit spikes at a somewhat reduced rate. And if I give an even smaller current, the spikes are even more spaced. So the frequency will look something like this. The frequency is high for high input, it's low for low input. And this is my function frequency as a function of input. Nu is a function of the input. So this is a single neuron property. I have one single neuron. I inject a current, I0, and then I record in that neuron the spike train, and what I will see is a sequence of spikes, of short electrical pulses, and this is the frequency as a function of this input current. Now we can do this for experimental neurons. We can also do this in model neurons. So this frequency current curve is available. But now let's go back to our network. In our network, we have many neurons. And now we have seen that each neuron is driven by a total input, which is a contribution of this network input and the external input. This is the input coming through the synapses within the network. And then this is an additional external input, maybe coming from other populations that we don't describe explicitly. So each neuron receives the same input. So each neuron will fire at this rate. So let's look at one of the neurons. These are the spike trains of one neuron. Maybe like this. In the absence of noise, the spiking would be very regular. If there's some noise, the spiking can be irregular. This is my first neuron. Now I have a second neuron that will also emit spikes. And I have a third neuron that emits spikes, and so on. I have many neurons. Each neuron emits its spikes. And let me just draw a couple of these. So in total I have n neurons. This is my nth neuron. So, as I said, in this population, each neuron receives the same constant input, and for this constant input, it emits a certain number of spikes. Say, we record for 1 second. This is 1 second. And the neurons fire with 8 Hertz. So typically, each neuron will emit exactly 8 spikes. So if I do this average for neuron 1 in this direction, I will get 8 spikes. If I do it for another neuron, I also get 8 spikes. So the firing rate as a temporal average is 8 spikes per second. Now my claim is that if you just look at a shorter interval, and now you count the spikes vertically in this interval between t and t plus delta t, if you divide by the number of neurons, and if you divide by this delta t, then it should also be 8 Hertz. Well, the reason is, if all neurons are the same, and if we are in a stationary state, then temporal averaging for a single neuron, or spatial averaging, is the same. So whether I have one single neuron, and I look for one time, and average over time, or I have one single neuron for look for a shorter time, and I do many, many repetitions of the same experiment, or whether I have n neurons, and I look at a short time, I always get the same result. Which means that this firing rate for a single neuron, which is the single neuron firing rate, is the same as the spatially averaged firing rate, A0, which is the population rate. Single neuron, temporal average, many neurons, spatial average, population activity. And this holds in the stationary state. Now let's put things together. So we have a first result that says in a stationary state, the input can be calculated from the stationary population activity, connectivity parameters, and some constant, and the external input. Then we have a second result that says the Fi curve or gain function tells me the firing rate for a single neuron for given constant input. And then I have a third result that says the single neuron rate is equal to the population rate. Again, this third result is just based on the idea that temporal averaging should give the same as spatial averaging if you are in a stationary state and if the network is homogeneous, which means all neurons are the same. So let's put all three equations together. The single neuron firing rate might be, for example, this curve here. It could be a slightly different curve, depends on the neuron type and the neuron model. This is my equation 2. I've taken this into account. Then I have my equation 3, which tells me that the vertical axis, which normally is the single neuron firing rate, can also be interpreted as the population rate. And what's still missing is equation 1. So let's work on equation 1. I have I0, just copy it, J0 Q A0 plus I external. I would like to plot it in the same plot. So I would like to pull out the A0. So I write I0 minus I external. I move this to the other side. Is J0 Q A0, or A0 is I0 I external divided by J0 Q. Now here I have A0 as a function of I0. It's linear in I0, and if for the moment I have no external current, then it goes through the origin. So what we find is there's a line, and A0 is a linear function of I0. That's the green function. This is the result of equation 1. Now at the same time, because of equation 2 and 3, A0 is also the red curve as a function of the total input. If all equations have to hold at the same time, then the solution is at the crossing points. So these are potential solutions where the network is in a stationary state of asynchronous firing. There's a low activity state and there's a high activity state. There's another one which turns out to be unstable. Now, what happens if we change the external current? If we increase the external current, we get a negative offset. So with an external current a bit bigger, we would only get the high fixed point up here. If I have a negative external current, then the green curve would shift upward and I only find the crossing point down here. Now what happens if the coupling is weak? So where is the coupling here? The coupling is the J0, is the coupling constant. If I change J0, make the coupling smaller, then the slope of this line gets steeper and I lose the other crossing points. So for weak coupling in the network, only a population activity at a very low level is possible, unless I have a strong external input, in which case I can still find my solutions that have a much larger value. So the message here is that in the stationary state, we can graphically construct the solutions of the population activity, which means we can predict the population activity for the connectivity, the J0, and we can predict the stationary population activity if we know the connectivity J0 and if we know the single neuron properties that are completely summarized by this Fi curve G of I0. So let me emphasize this. We have had a homogeneous network, which means all neurons are the same. We are looking at the stationary solution, and these conditions allow us to exploit the fact that the single neuron rate is equal to the population rate. Then I can go for a graphical solution, or alternatively, I can find the solution numerically. The activity is equal to the single neuron firing rate, which is a function of I0. I0 has this expression, but this expression contains the population activity. So I have a loop from the population activity, which gives rise to the population activity. What I've shown you is the graphical solution, but if you are on a computer, you can also numerically solve for the stationary states of asynchronous firing in this homogeneous population that's fully connected. Now, an important role plays this function g. But what is this function g? Well, you can calculate it, for example, for a leaky integrand fire neuron with or without noise. You can calculate it. For a spike response model, another form of integrand fire model, you can calculate it. For the Hodgkin-Huxley model, you can simulate it. Most importantly, for real neurons, experimental neurons, you can also measure this gain function. So, of all the many different neuron properties, once you are in a stationary state, the only thing that matters is this Fi curve, the frequency current curve. What matters is this function g. So once you have the connectivity parameters of a neuronal population, you can predict the population activity based on single neuron properties. And the relevant single neuron property is the Fi curve, which itself may depend on the noise level that you have in your network. So let me summarize what we have seen so far. We have looked at a single population. We have assumed that it's homogeneous, which means all neurons are the same. They have the same parameters. They are of the same type. We have assumed full connectivity, and we looked at the stationary state for asynchronous firing. And then we exploited that the single neuron rate is equal to population rate, and we could just write down the formula for the population activity, and we could solve it graphically. Now, the important thing that you need is the gain function for single neurons for constant input, and that's available. That's available for most neuron models, and importantly, it's also available for most experimental neurons. However, please note the whole approach that we have used here in this section is limited to stationary state, constant activity. Now, in reality, the brain will never be in a stationary state, but it's nevertheless interesting that it's possible to predict these values of asynchronous firing in a stationary state just for model parameters. The second limitation has been that we looked at a fully connected network, and this is the restriction that we will drop in the next section. So please stay on and let's continue with section 6.